Okay, so how are we actually going to use this formula? What's it mean? So if we recall, we've got this cross-sectional area, our neutral axis. We're looking at a position slightly away from it, y distance. Our width is t, and we knew we were integrating delta y, and we were finding the force that's going to be in effect there for this section here for the area. So I've got a force going upwards. So that's going to be this whole section here. It's located in terms of its centroid will be at this point here, and then if I integrate all this force, I can then say that the shear at this point is going to be given in those terms. So the Q is going to be the first order integral of this area, delta y, delta z, where we're looking at the start location and we're going all the way to the top. Let's say if we're above the neutral axis. So that's what the Q is. Let's do an example for a square. So we've got a square, L, like that. So if I want you to know what the shear stress is at this location y, the first thing I'd do is I'd find my Q. So integrate y by delta y, delta z. Z stays constant and then it becomes an L, so we're just integrating y by delta y. The start location is the lower location, y, and we integrate it all the way to the top, y top. Arbitrary location I'll do this for, so we'll do it for y. L top, so y top is going to be L divided by 2. You need to integrate that. So that's going to give me L over 2 y squared L over 2 from y. So Q is given as L over 2 L squared over 4, take away y squared. So we then can dump this into our formula. And that is that the shear stress is given as VQI over T. So we've got VI. T in this particular case is going to be L, and the Q we worked out to be L over 2 L squared over 4, take away y squared. So the L's cancel, so we need to know the shear stress, we need to know the shear force, second moment of area, put the 2 there, I'll leave it like this, L squared over 4 y squared. So my shear is going to be given as a maximum when y equals 0, That's going to give me what? A value of V L squared 8 over I. Okay, so that would be that value there. And when y equals L over a half, it will go down to 0. Okay. So we end up with a parabola result with respect to y. Well, we get maximum shear occurring in the middle. The maximum shear is this value. So what else can I tell you about this value? Well, I know what I is. I is going to be L to the power 4 over 12. Yeah, so I'm using BD to the power 3 over 12. So B equals D equals L. So this becomes 12 over 8. 12 over 8, which is divided by 3 top and divided by 4 top and bottom, gives me 4. No, it doesn't. Gives me 3 over 2. The L squared divided by L squared equals 3 over 2 shear force divided by L squared. So if I was making previously assuming what the shear force would be along the bar, I would have guessed that it would be the force being that I'm seeing at this point, and it's going to be 2/3 of the maximum. So that's where my shear average is, and this is where my shear maximum is. So if we were just doing a simple beam and we'd had a kind of shear force diagram like this, the V that I would be using would be this force here, so that would go in there, and I would divide it by the area of my beam, and I would therefore tell you, okay, the shear force is going to be V divided by L squared. Well, in actual fact, with this analysis, we see that the shear force actually peaks in the middle of the beam, and the value that I've calculated, if I just take it from the shear force diagram, will give me the average shear force. And the difference is 1.5, so we're looking at 50% higher shear force if we were basing our calculations and structural integrity calculations just on that calculation there. Okay, so that means we have to be a bit careful for when we're, if for example shear force was important in our structural integrity of our well, in this case our beam or bolt or whatever it might be.